Hello everyone, welcome to today's tutorial on simple harmonic motion, the undamped case. So we have three cases: a spring hung from a ceiling before loading, at equilibrium after loading when the Hooke's law has acted upon it at gravity, then the one in motion when it's now oscillating about the equilibrium position O for case 2. That's the equilibrium position, that from Hooke's law, T is equal to Ke. Tension is proportional to extension. And from Newton's second law, you have that all the forces acting on it must be equal to Ma. But in this case, there is no acceleration because it's at equilibrium, it's stationary, so it's zero. So, and the forces acting on it is tension and the weight of the body. So you have a T minus mg, because if this is positive side, this is negative side pointed downwards, and we have said that T is equal to Ke. So if we substitute it here, we will now get Ke is equal to mg. Okay, case 3. So the spring is now in motion. So we say that Hooke's law is equal to K. The extension now is E plus X. So Hooke's law again, Hooke's. So from Newton's law also, we have that sigma F is equal to ma. It is now accelerating. So in this case, we will have that T, the tension in the string, minus Ke plus Kx is equal to ma. And we have said that T is equal to Ke and is equal to that. So we put it, we have Ke minus Ke minus Kx equal to ma. So we have that minus Kx is equal to md squared x over t squared. This is the equation of a motion. So we can write it in this way: d squared x over dt squared is equal to minus k over mx. Remember that when we dealt with a motion in a circle, we said that the acceleration is tending inward, and we got that acceleration to be a is equal to v squared over r. V squared over r. So if the radius is x, it will be v squared over x. So that when we now add it, and we also said no that v is equal to 2 pi r, 2 pi r, 2 pi x in this case over t. That's equal to omega x, omega x. So if we now put this into here, we see that a is equal to omega squared x squared over x. So we have it to be omega squared x. That's what our acceleration will be. Therefore, it means that ma is equal to minus kx, and it's equal to minus m omega squared x. So that we can easily see that if we bring this one here, we see that it's equal to, that's minus kx over m is equal to omega squared x. That's if we remove this. So that our d squared x over dt squared is equal to minus omega squared x. So, or this, either this or this, depending on the one you are using, but let's use the one with angular frequency. This is a homogeneous equation, a second order homogeneous equation that we can solve. So we can say that is x prime prime plus omega squared x is equal to 0. So we can solve this homogeneous equation. To solve this homogeneous equation, we say let this be m squared plus omega squared is equal to this. M is equal to minus omega squared, and this implies that m is equal to plus minus square root of minus omega squared. The solution now becomes either m is equal to 0 plus omega I, or 0 minus omega I, because you know that this one will be omega here, square root of minus 1, and square root of minus 1 is I. Therefore, general solution will be of the form x of t is equal to e alpha t, the constant 1 cos omega t, plus c2 sine omega t. That's how to the solution, where alpha is 0. So if we substitute 0 into this equation, we'll get x of t is equal to, of course you know that is 1, c1 cos omega t plus c2 sine omega t. That's what we have. So that the true solution is x of t is equal to c1 cos omega t plus c2 sine omega t. I want to solve this analytically. This type of equation appear in many practical problems in physics and engineering, and we can write it in this form, and it can be written in this form: a sine omega t plus phi. It can be minus, this thing can be plus or minus, or remember s of t is equal to, or x of t is equal to a cos omega t plus minus phi or plus phi. Let's use plus phi since we are using this. So this thing is x of t. So we can easily prove this. So to prove this, that these equations are correct, we say let this be this. Let this be our solution. Let this be our solution. I just want to prove it. So if we say let that be our solution, we say let a cos omega t plus phi equal to c1 cos omega t plus c2 sine omega t. And you know that cos omega t is a into cos omega t cos phi minus sine omega t sine phi is equal to this equation above. So that we can see now that from here we have cos omega t. That means that therefore c1 is equal to a cos phi, a cos phi, and c2. Okay, let's say put this one minus. If we put this one minus, here will be plus. We'll put it minus. Okay, so that our c2 will be a sine phi. c2 will be a sine phi. So let's remember, I told you that this thing can be plus or minus. It doesn't matter. So that from here you see that if we do c1 squared plus c2 squared, we have a squared cos squared phi plus a squared sine squared phi. So that you see that if we factor this, it will be a squared into this plus this 1. So that a is equal to square root of c1 squared plus c2 squared. Then that equation will be, therefore x is equal to x of t is equal to square root of c1 squared plus c2 squared cos omega t minus, since we used minus to obtain this, minus even if we use plus in this one, it will be minus. When you square it, it will still be plus. So phi. So you see that we have replaced these constants here and made them to be one single one of these, and we got this from a cos omega t minus phi, omega t minus phi. From here, from what we have gotten here, from what we have gotten in a this and this, you see that you can get tan phi. Tan phi will be a sine phi over a cos phi, and a sine phi is and a sine phi, this one is c2, and a cos phi is c1. So you have that tan phi is just the constant c2 over c1. Thanks for now. Please subscribe and keep tabs on one or two problems that we will solve. Bye.